Alright, silly people, here's the situation. We have a square potential well of width W and height V, and we're going to be, finding the energy levels for it numerically. First of all, by actually just plotting these three functions here, y1, y2, and y3, which will help us find the approximate solutions for the energy well, given this behavior here. So, it is just a plotting problem for the first part, so it's going to be fairly, uh, routine considering this textbook as DLT. So I'm going to define some functions, y1 of e, which is going to return, I better define some physical constants as well. So W is 1 nanometer, V is 20 electron volts, but I am going to convert to joules for this and then convert back to, EV at the end. The mass of the electron is 9.1 E minus 31, and also H bar is 1.054 E minus 34. Right. Okay. It's going to return the tangent of the square root of W squared, which I'm going to also put in its own parentheses, times M times E divided by 2 times H bar squared. Sure. Then define y2 of E, which is going to return the square root of, in parentheses, V minus E over E, and then also y3 of E, which is going to return minus the square root of E over, in parentheses, V minus E. Right, we can define an input list for this to run through. I'm just going to call it ELS. It's going to be the lens space between 0 and 20 eV, but I'm going to convert that to joules as well. And then 1,000 points for that for high fidelity. And then also, just do some plot lines now. I'm going to plot ELS, and I am going to actually divide ELS in the plot line by 1.6 e to the minus 19 to convert it back into electron volts for the plot. But then each of the y functions are dimensionless, so we can just plot it against y of ELS, right? I'm going to copy this plot line down a couple more times to do y3 and y2, and I'll tell you right now that the tangent function here is problematic because tangent, tends to shoot off towards positive or minus infinity if the argument in it is about pi halves. So I'm going to convert, or I'm not going to convert, I am going to limit, though, the y-axis here to only run from minus 10 to 10. So we don't have it shooting off to like infinity when we're trying to look at it. But okay, here is what that plot looks like. Now what is this? How do we get information out of this? The solutions for the energy states are going to be here, 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 and here. Wherever the green or orange lines are crossing the blue line when the blue line is varying smoothly. So don't count up here or here or here or here. Those are where the value is actually just dipping. It's not a physical value. So just the parts where the lines are crossing and they're both varying smoothly. Right. So that actually represents the first 6 energy states. So E1, 3, and 5 for the green line, since the green line is this guy, is for the odd numbered states. And then 2, 3, and 4 are 2, 4, and 6 for the orange line, because the orange line represents the even numbered states. But now we actually have to find what those solutions are using binary search. So to do that, I'm going to do it in this same code cell here. I'm going to define 2 different functions to help us do the binary search. One of them is going to take care of the even numbered states, and one is going to do the odd numbered states. Let me do the odd first. Call it def odd of x1 and x2, because it is just going to do binary search. I want to be able to guess initial values, like in between here, in terms of EV, so I'm actually going to multiply my guess by 1.6 e minus 19 to convert it into joules before it starts doing math. Same for x2. The accuracy that Newman wants us to get down to is 0.001 EV. So I'm going to define it as 0.001 times 1.6 e minus 19 joules. And then always just set the error to an arbitrarily large number. I always do Avogadro's for no reason. And then, yeah, start your while loop while error is greater than your accuracy. Then you will calculate a midpoint between x1 and x2. And that's like that. And at this point, you would check if the function that you're solving is, the function at the midpoint and the function at f1. If they have the same sign, then you set x1 equal to the midpoint. But the function that we are checking is, the blue line, so y1. For the odd numbered states, you're checking for the solution against y3. So you solve it for 0, so you have y1 plus y3 equals 0. So okay, let me do y1 of the midpoint, and this is all going to be in parentheses. And I think it's minus that. Yeah, minus y3 of the midpoint. If that happens to be the same side as y1 of x1 minus y3 of x1, so if it's greater than 0, then you set x1 equal to the midpoint. Otherwise, you set x2 equal to the midpoint, and at the end you can have it return the new midpoint between those, so x1 plus x2 over 2, and make sure to have a line where you're calculating the error in here. So the error is always just going to be the absolute value of x1 minus x2. Okay, so that's the one that's going to help us find the odd numbered energy values. Also define a function called even, which is going to do the same for the even numbered energy values. And it's pretty much the same idea. So I'm just going to copy this down, except you're going to put y2 here, because for the even numbered states, you're solving the equation of y1 minus y2 equals 0, right? Okay, so y2 here and y2 here. At the end, we can print out a bunch of energy values, so print, let's do E1 first, which is, of course, going to be running odd of, let's see, where is the first solution going to be? it's going to be in between like 1 and 2. We'll do, yeah, 1 and 2. That's fine. And then it's going to print out the, oh, we want to convert it back into electron volts for the end. Newman wants it in electron volts. And then also going to print out EV here for units. Let me copy this print line down and do the same thing for E3 and E5. So where do I think E3 is going to be? I'm thinking between 4 and 6. Let's just put that in 4, 6. And then this guy, probably in between 10 and 13. Let's call that 10 and 13. Now I can do the even numbered solutions. So E2 equals even, and then I'm going to divide the solution by 1.6 e minus 19 and give it the units of EV. But where do I think the first even solution is going to be? Somewhere between 2.5 and 3, sure. Somewhere between 2.5 and I don't want to get like too far away because there's this like discontinuity here. Maybe I'll just make between 2.5 and 2.8. 2.8 here. And I'm going to just copy this line down again. E4 now. I'm going to calculate in between 7 and yeah, let's just do between 7 and 8. Why not? 7 and 8, and then also finally, whoopsie daisy. We'll check for E6, which I want to say is between like 13 and 16, somewhere in that range. Yeah, okay. Let's see if that prints reasonable values. Hey, look at those. So do I think this is 1.27? I'll buy it. This is about 2.8, it says, so sure. This is going to print out like about 5. Yeah, I believe that. That says about 7.8, sure. This is 11.22, yeah, that's fine. And this is 15.08, yeah. These are all reasonable values, I think. All right.